So how do you remove this? How do you, what condition do you put so that that relation is symmetric? You know what I'm talking. This relation called two elements X and Y. It is a relation between V and W. So X related
So
to Y.
when V equals to W?
No. In general, do you have you know the concept a relation from a set A to from a set A to the set B? Hello, Sonakshi.
Yes, sir.
You in general you must have heard when we have two sets A and B. Sets. Then what is the relation R from A to B?
So maybe you can
So
put.
it is an ordered pair.
Yes, and then you take A equal to B, and then you can talk about symmetry.
Yes, sir.
All right. So in that way.
So,
Yeah, Ishan, you had some problem?
no, not problem. You had asked what we could do to make it symmetric. So I had an idea. I'm not sure if that was. So I was thinking the problem was you wanted if V and W, if V is related to W, you want W related to V. So
No,
maybe
but
you.
now you, as you say, we have to take V equal to W.
No, so what can we do to avoid that? So one of the things I thought is we can
So
put.
therefore, we have to put a condition on the form.
Yes, or so we could use tensors to convert it to go from. So you had a bilinear form.
I
So
didn't, okay, I didn't have bilinear, I have sesquilinear. So
okay, sorry.
the thing we started with, phi is from V cross V to K. And we had this sesquilinear form.
Mm-hmm.
And I am talking about this perpendicular relation.
Mm-hmm.
This is not symmetric in general. So I will put a condition on the form so that it becomes symmetric.
Okay.
So that condition is precisely so that will lead us to the definition. So the definition I want to I will take V to be finite dimensional. V finite dimensional. We say that phi is Hermitian respectively skew Hermitian if phi of xy equal to phi bar of yx bar, phi yx bar respectively phi of xy equal to minus phi of yx bar. This is the definition. Now here I want to make one very strong comment that note that what is our assumption. Our assumption is, so remember our assumption. This is very important. Remember our assumption, because when you read other books you will get confused. Remember our convention. What was our convention? That kappa on k, the involution on k. What are we assuming about that? We have two cases that we are interested in. when kappa is identity. In this case, we are assuming, I am going to assume further that characteristic K is not true and kappa is non-identity. In this case, I am not going to assume anything. So no other assumption. And of course, kappa square is identity. So now if you read with this, if it is identity in this case, so then in this case I will write here only. These are also two cases, no? In identity case, it is just phi by x, or this is identity case I am writing minus phi by x. This is kappa is identity case. And then we know that this definition means symmetric bilinear. This is symmetric. Phi by x, that is symmetric. And this case is skew symmetric. That is what the standard definition you learn. Okay, now if kappa is not identity, then it is this conjugate condition, real conjugate. So therefore, actually when I have written like this, in this case, Hermitian means symmetric and skew Hermitian means skew symmetric. That is typically this case occur when you are studying this bilinear forms or real numbers. When the field is real numbers, you have no option. This option doesn't come. And when you are studying or complex numbers, it is really, and kappa is not identity, then it is Hermitian and skew Hermitian. And this Hermitian actually, I am not sure I should write this H maybe capital.
So can I ask something, please?
1 minute, I will give you a chance. So yes, these definitions, these are due to Hermite. Charles Hermite. Yes, now you can ask me.
So the finite, you started off with V finite dimensional. I don't understand yet why that is necessary.
Of course, the definition will make sense even when V is not finite dimensional. But the problem is when we convert to matrices, then the thing will not be present in the finite dimension, in not finite dimensional case. And see, at the same time, if I have too much general, then also the problem comes with the motivation. So slowly you do it. Let's master the finite dimensional case and then go over to the infinite dimensional case. And then in that case, there will be, of course, the theorems will not be dicto true because characteristic polynomial may not make sense. Minimal polynomial you don't know. And all these things will crop up. So I suggest you take one. We assume it's finite dimensional and then do it when you are fairly got enough experience. Then you think about what happens with not finite dimension. All right. So now why do this? See, for example, when you want to study symmetric bilinear form or complex numbers, this case is also included here. That is this. This is R, K equal to R and K equal to C. They are included here and this is K equal to C. And if we make our statement definitions combined and this is our convention, then lot of theorem which you get same proof repetitions that you will get at once. That is what we will see now. This lecture and tomorrow's lecture. If anybody has any doubt still? Yes, please. Tithi. Tithi?
Yes, sir.
Any other doubt you have in your mind?
No, sir, it's fine.
All right, but this is Very important. I will keep calling them Hermitian and Skew Hermitian, but that's hidden in our convention that they are symmetric and skew symmetric. And these, when the distinction come, these cases I will call complex Hermitian and complex skew symmetric, skew Hermitian. So in this case, I will also use sometimes the adjective complex. That doesn't mean this is addressed to these complex numbers, but to this such a field. All right, and I think the time goes, it will be clearer. So now this definition, if you take your sesquilinear form to be Hermitian or skew Hermitian, then obviously this perpendicularity relation is symmetric because of this definition. All right, now what do we want to do with this? First, I should give you some example. All right, so I will give, also I will have to introduce definitions, new definition. All right, so now suppose you have phi is, now it is clear when I say phi is Hermitian. Sorry?
आगे कुछ देने टाइम लग गया और बाकी सब ठीक.
Hello Rohit. All right, if he is Hermitian, or this will also work for skew Hermitian. So really there are 4 cases in our setup. Now, in this case, you remember phi1. Phi1 is from V to V star. And phi2 is from V to V star again. Because this phi is, we are taking Hermitian form on V. That means this is a V cross V to K. Linear in the first variable and semi-linear in the second variable. And then this V W, so this is V to W star, and this is W, and this is V star. In this case, what will happen that phi1 is phi2 in the Hermitian case, and in the skew Hermitian case, it will be phi1 equal to minus phi2. This is just a definition. And then what will be the perp? What will be the V perp? V perp on this side and V perp on this side. This is precisely the kernel of phi1. And this is kernel of phi2. And they are equal. And this is called degeneration ideal. Okay. Degeneration, not ideal space of that will measure how far that phi is from the duality, non-degeneracy. So this is radical. This is also called radical of phi. These are just definitions, but we should see now the examples. And the one thing we can convert this into matrices and then we can write down. So phi is Hermitian if and only if the Grams matrix of phi with respect to the basis x. So there's only one basis, no? I am taking same basis here in our earlier notation, if you like. That Grams matrix is what? That is the matrix phi evaluated at xij. This is I, comma j, they belong to I. I is the, if you want, 1 to n, and this x is the basis, xi. This Grams matrix is Hermitian. And similarly for skew Hermitian. Hello, Rohitesh. Rohitesh. Hello, Rohitesh. Is he attending a lecture or he is giving a lecture somewhere else? I don't know. Skew Hermitian. So one should recall what is this Hermitian matrix. So that is, so a matrix A, square matrix is called Hermitian if and only if, what is the definition? The matrix A, on the other hand, you take a transpose of that and then the conjugate, they are same. And skew Hermitian, A is minus of this. It is skew Hermitian. And therefore, our definition of symmetric matrix is contained here. If it is symmetric, that means our conjugation is identity. That means bar is equal to itself. So in that case, symmetric will be A equal to A transpose, and skew symmetric means A equal to minus A transpose. All right. And as I said, when I exactly want to stress the second case, this case, I will say I will use the adjective complex. That should not give you any confusion. If anybody has still doubt, they can raise it now. All right, so I want to give some examples. And what is it that we want to prove? The first theorem ever I want to prove is, what do I want to prove? The first theorem. That is the decomposition theorem. That I want to decompose this form and to study like that, and then study the automorphisms and so on. So now, what will be the about the first of all about the basic change and so on. So let me write down that statement. That is also very useful when you convert from in the coordinates. All right. So if you have a basis, if you fix a basis, I want to write down the map from where to where. So remember our notation. This K prime, I will call it as a fixed field of kappa. In case of complex number, K prime is R. But if you are, for example, if you are taking a finite field, that is also very interesting. And then if you taking the quadratic extension of a finite field, then you will get that finite field. So all this was created by Jordan, remember, and Jordan's motivation to create all these things was to study Galois theory or use this in Galois theory to understand Galois theory better. Because those days there was no linear algebra, was not so much. All right, so if you take the map phi forms to the matrices G phi x. This is the map from where to where? This is these all Hermitian forms. They see all Hermitian form, if you take, that forms a vector space. And these are the matrices. They also form a vector space. So this will be an isomorphism from the K prime vector. See, these all forms. So let me write it. So I don't want to create more notation, otherwise it will be complicated. So if you look at all Hermitian forms, Hermitian forms, 1V, all of them. That is a vector space. Vector space over room over that fixed field. And I will write only Hermitian. Similarly, you can write skew Hermitian. There is no big deal. So this is an isomorphism. This one is from this vector space to where? To the matrices. To the matrices. See, these are not all matrices. These are Hermitian matrices. And this one is an isomorphism between them. And this is, we have chosen a basis. Now the question is, when you change a basis, what happens? And then you know the answer actually. So if you change a basis, what happens is this grounds matrix and this grounds matrix, the other one, G phi x bar prime, how are they related? They are related by a matrix A transpose on this side and A bar on the other side. These are called congruent matrices. And this one is a basis, change of basis from x to x prime. No, this one is, yeah, x to x prime, and then they are related by this we saw earlier. So this is, so one could play around. If you want to choose a basis, you can go here and study the matrices and convert it. That is why I stated this. And the proof is more or less obvious. Also, the important case is another thing which helps you in the calculation is the following. See, there are important cases of sesquilinear forms which are completely determined by its values on the diagonal. So I will write here important cases of sesquilinear forms. We will see that immediately after this. Sesquilinear forms on V are determined by their values on the diagonal only. Diagonal V, that is XX. So the next proposition will remind you that you would approve this in your linear algebra course, especially when you did inner product spaces. Inner product spaces are much specialized example. These are also known as polarization identity. So, what is the polarization identity? We are assuming first case I will write. We are assuming I'm splitting the two cases for understanding. So kappa is not identity. And remember phi is a form. Then what? For all x comma y, for all xy in V cross V and A scalar such that which is not the bar. That is possible because we are assuming kappa is not identity. Then I want to compute the value of phi xy. By using the diagonal values. Understood? So I want to write this as, maybe I should have written the easier case first. So we will come back to this. Let me write the first easier case. Second case let me write and then we will come back to this. So in this case we are assuming characteristic K is not 2 and of course kappa is identity. This is a symmetric case and this is complex Hermitian case. Then and also phi I have to tell you phi V cross V to K symmetric bilinear. Form on V. Then I want to write phi xy in terms of the diagonal elements. That is what I said, important cases of sesquilinear forms, they are determined by only the diagonal values. That will make the life more comfortable. So this is the first case, this is the second case we'll write first, and then we'll go to this little complicated case, but that is similar proof. So then what? For every xy in V, I want to write a formula for this in terms of the diagonal case only. So that is, I am allowed to take phi of x plus y, and phi of xy, xx, and phi of yy. These are all diagonal values, right? And you know the relation. What is the relation? This is half of this minus this minus this. Is that clear? This, if you expand it, it will be clear. Symmetric, so and bilinear. So you expand this and you cancel, and this is very easy to check. You would have checked that. So that shows, that proves by this comment that they are determined. Symmetric bilinear forms are uniquely determined by their values on the diagonal elements. And this you can further write it down. This equality you can further write it. This is 1/4 phi x plus y minus phi x minus y x minus y. Right? And that is why you remember this assumption. Why do I keep saying I wanted to do this? So this assumption is very important for studying symmetric bilinear forms. Otherwise, things will go wrong. All right. So now I want to write the more general statement here. So what is the? Let us write more precisely. Kappa is not identity, and this is Hermitian form. This is complex Hermitian. And this complex word doesn't refer to the complex numbers, please. This refers to the fact that kappa is not identity. And now I want to write such a formula. See, the aim is to write such a formula. So what will be the case? It's a little complicated, but I will write one and then see whether it is just merely will be the checking. So obviously here there are only two guys involved, three guys. So there also you will have three only, or four. In this case there are three, but in this case there are four because that A is also coming now. So what will be the? This will be equal to, I will adjust the scalar later. So this will be phi of ax plus y, ax plus y. We want the diagonal guys only. Minus phi of x plus y, x plus y. Of course, minus phi of xx minus phi of yy. And I want to adjust the coefficients so that the equality holds. That clear? First, don't worry about the calculation. See, what we want to do, that we have to understand. My aim is to write arbitrary value of phi on arbitrary pair xy in terms of the diagonal values. So obviously, if A is given, then these are the diagonal values I can take. And obviously, then you may ask me, why did I choose this year and not in the next? You can choose in the next also, but your calculation will become little more complicated probably. So now I'll write down the coefficients. So the coefficients are, this is similar to this calculation. All right, and I will not check, but I will give you a hint. So this is A bar. This is A bar times A minus 1. Or not minus, before minus I should have done. This is minus comes before, and then A bar A minus 1. That is the coefficient of this. And here it will be 1 minus A bar. And now when you expand this, you will realize that you will need this half, this. Then also you will need to adjust the role of this half. That will be 1 over A minus A bar. And there is no characteristic involved now. This A minus A bar makes sense in K. Because A bar is not A. And now this checking you do it. This is nothing. Okay, and then how do you assure that such a coefficient exists? So you can, in principle, what you could do is you can write some coefficient, some A, some B, not A, some lambda, mu, nu, and eta, and then look for how do you solve the system, and then you will realize that you will have to use somewhere Cramer's rule, and then you will get exact solutions. That is one way, or at least most of the students, even when I was in the college, we just took the book and verified the formula. We didn't bother about how it came, where it came from, we just blindly checked. So I will just write here the word Cramer's rule. Will help you that such a thing exists, and then you can find those coefficients actually, and then check if it is correct. Okay, this is XY formula. What about the other? Because we have to check the other also, because there is only complex Hermitian. What is the difference between this and this? They are not equal. But you know, in case of complex Hermitian, this will be the conjugate of that. So therefore, you can write the conjugate formula. So this will become conjugate, A bar will come first, A will come later. Similarly, this. So that also you can write down the formula. You can just copy it from here. This is the polarization identity. These are called polarization identity. When you have time and you go back, you can see the book. And now I would say that you should see the right book. I don't know what are the books in your curriculum, but can somebody tell me what are the books in your curriculum for linear algebra or bilinear forms you use it? Hello, Sonakshi.
Sir, in my coursework, I have a linear algebra done right by Sheldon Exler.
I don't know whether it contains. That is a new book to me. I don't know. But I would recommend you to look for Jacobson's book.
Okay, sir.
Jacobson is
Which of Jacobson?
Very good book. And Jacobson has 2 volumes, Basic Algebra 1 and Basic Algebra 2, and this might be in Basic Algebra, I don't know, because I didn't read these books. Our time, these books were not there. They were lectures on Abstract Algebra 1, 2, 3. And that is the one which were prescribed to us in a college as well as in the first year masters. All right. So what is the immediate consequence? The 2 corollaries. So I am not going to prove this, but I will write 2 consequences. Corollary 1. So if you want to check phi is a form V cross V to K. Sesquilinear form. On V. And I am in the second case, that is kappa is not identity. Then phi is Hermitian. If and only if phi XX equal to 5rxx for all x. And similarly, skew Hermitian. Skew Hermitian respectively phi xx equal to minus phi x bar for every x. With v, not x. You see here, obviously, when somebody gives you a form and say check it is Hermitian or skew Hermitian, how do you check? I mean, of course, you can try to check it is bilinear, first variable linear, second variable semilinear, but this is the quickest way to check because you don't have to involve the second coordinate is x. In particular, what is the advantage? Another one. In particular, if your form is complex Hermitian, if he is complex Hermitian, then all these diagonal values, they are in the fixed field, which we have denoted k per n. So in case your field is complex number, then they are real values. And the same thing for the same thing is not for the other skew Hermitian case, they are purely imaginary. Similarly, write down the statement for skew Hermitian. The values are purely imaginary. And this term also makes sense for arbitrary k with identity involution, non-identity involution. All right, and the next corollary will be for the other case when kappa is identity. So corollary 2, when this is the case when kappa is equal to idk and form, this is a sesquilinear form on V is symmetric. Now we'll use the term, and of course we have to assume characteristic k is not 2. Is symmetric, bilinear form if and only if the diagonal values are 0. No, I don't want to write diagonal values are 0. This symmetric form is equal to the 0 form if and only if the diagonal values are 0. Once the diagonal elements are 0, then actually it's a 0 form. All right, so with this, now what I want to do is the following. I should also discuss some examples because this is going on without examples, which I don't like it. All right, so maybe before that I should discuss some examples. Let us discuss some examples so that at least you will have some examples in hand. But for examples, I will need some definitions. All right, let me make a definition. This is to write down examples. Definition. So V is a vector space as usual, and I am taking phi to be, actually I should take both, but let us take symmetric bilinear form. On V. And let us take a vector in V. You call this vector to be isotropic. Again, this word is coming from physics with respect to phi. If x is perpendicular to itself. Now this doesn't happen in our Euclidean geometry, but it is very useful. That is, you will see in example below that. And if you look at all isotropic vectors with respect to phi, that is, you can look at all x, so that x is perpendicular to x itself. This is called isotropic cone, or also it is called a light cone. I will show you in a few minutes in example that where do this come from with respect to phi. That is the first definition. And second one, we will call phi to be the vector, the form to be anisotropic and isotropic if there is no perpendicular vector. If there exists no non-zero x in V such that x is perpendicular to itself. That means the light cone is just a trivial. All right. Now let us see an example. This example will throw light why we defined like this, why the terms are useful. This is called Lorentz form. This was very important in physics. And there are many forms. They are named after Lorentz. All right, where you can see the non-trivial isotropic vectors. All right. First, I will give you the standard Lorentz form. Standard Lorentz form. And remember, when I say standard Lorentz form, that means I will give the example on a standard vector space. That means I have given the coordinate. So what is the standard vector space? I will take V equal to Rn plus 1. N is any natural. And I will give the grounds matrix with respect to the standard basis. So the form on V Rn plus 1 with grounds matrix. Because we saw if I give you the grounds matrix, that will define a form. And what is the matrix? That should be now n plus 1 cross n plus 1 matrix. N plus 1 cross n plus 1 matrix. And also it should be symmetric. Because, all right, so that matrix is the following. Minus c square 1, 1, 1 on the diagonal, and everywhere else it is. And where C is real number, of course, and C is positive. This entry is therefore negative. And that C, where do that C come from? That comes from the velocity. All right, so let me see there. In this case, this C is, if you have studied a little bit physics, this C is velocity of light. Which you can normalize when equal to C equal to 1. That is normalized because normalization means you have changed the basis so that that entry become -1. All right, now what is the light cone in this case? Now the variables I will write what? How will I write the variables? I will write that separate variable, that is R. So Rn plus 1. I will write it as R cross Rn. And then I want to describe you which are the, what is the light cone? That means which vectors are perpendicular to themselves. So that we will write down. That is, now you consider the vectors. Now this variable I will write it T, and then I will write the tuple A1 to AN in Rn with what? The perpendicularity relation will tell you what? That will tell you A1 square plus AN square equal to T square. Where do this come from? This comes from that relation. That is, this is coming from the fact that phi xx is 0. You compute phi xx, use this matrix, compute phi xx, compute phi, this is your x. Compute that. You know this, you know the values, so you compute that. And then you will see, here, phi tt will come and others are perpendicular, so you know you will come back to this. So this is precisely the light cone. So light cone in this case is light cone equal to this T A1 to AN such that A1 square plus AN square equal to T square. So if you try to draw the picture for n equal to 2 or n equal to 2 or 3, n equal to 2. See here, it will look like this. I will try to draw the picture. N equal to 3. N is 2. So n plus 1 is 3. So this is my t-axis. And these are. So this is the picture for C equal to 1. So the cone you are seeing, that is the cone. This cone. Also you will see, if you see that, also you will see a nice thing that if you take the line passing through this point, 1 minus 1, and that line is perpendicular to itself. All right, now the question comes now. It's already time is coming up. Question comes. How do you reduce? How do you get? I want to ultimately what I want to do. I want to decompose. See, the idea is I want to decompose this vector space in such a way that I can classify them. Okay, so to be more specific, remember classification of linear maps. I'm just listing these you would have dealt in. Or remember, we have also dealt with in the earlier part of the lecture, we have classified all homogeneous spaces. We have classified all simply transitive spaces. Classified. We know the list of them. Similarly, in your whole linear algebra course, you would have spent time to classify linear maps. Haven't you? Yes, Roshni? Are you there? Hello, Roshni.
Yes, sir. I am there. I was just thinking what you were telling and I could not.
Have you studied what is classification of linear maps in linear algebra on finite dimensional spaces? Can you list all linear maps? Sonakshi?
I'm not, unable to recall them right now. Can you please give more description? What do you mean?
I will give you just a moment. I want to ask few more so that I should not feel that. What about Ishan?
Sir, if you're talking on the basis of the JCF.
No. I am just asking very simple question. Can you classify all linear maps on a finite dimensional vector space?
Yes,
I can tell you how to look once I know the JCF of the thing, but otherwise I'm not sure what you mean, sir.
Classification, do you understand? What does one mean by classification?
Yes.
What does that mean? You give a list. These are all linear maps. Or in other words, give an equivalence relation on the set of linear maps and describe their orbits.
Oh, sir, I can't think of it.
Have you heard of Jordan form?
Yeah, I was talking about that's what I was saying, JCF. On the basis.
I don't know your short form.
Oh, okay. I meant Jordan canonical form. That's what I was talking about.
Jordan canonical form precisely addresses this question.
Yes, that's why I said on the basis of the JCF, I can tell you about the linear map. So I meant Jordan canonical form.
Yes. And the whole linear algebra course, what you are fed probably in the first course leads to that classification. And in every subject, classification problem is there. Every subject. Now you see, for example, you remember in the first part, I have classified you all homogeneous spaces. I classified all simply transitive G spaces. So did we not? Yes or no?
Yes, sir.
We have proved that every homogeneous G space is isomorphic as a G space to that G by H left coset space and so on. And now if you go to topological spaces also there is a classification, but that becomes more difficult. Yes, the problem becomes more and more difficult if you go to simple or difficult if you go to different subjects. Now if you want the classification problem in topology should be what? If you take some invariant and then say that whether can you list all topological spaces up to homeomorphism. Right? So now my problem is we have classified linear maps, and now I want to classify all Hermitian and Skew Hermitian forms. That these are the forms. Is that clear? That is what I am up to now. I want to use this. I want to classify. So problem is to classify all Hermitian, respectively, Skew Hermitian forms. That includes symmetric and skew symmetric. Hermitian, when kappa is identity, it is symmetric or skew. All right, now what am I supposed to use? What did I use in classification in linear maps? What did I use? I use characteristic polynomial, I use minimal polynomial, and I use the multiplicities of their zeros also. And their zeros also I use. So that was allowed to use. So this classification was in terms of those invariants. So you see, this is in terms of what is given to you, the invariants are given to you. And what are the invariants of linear maps? So I will write down the invariants. So in this case, we have chi f, we have mu f, we have their zeros. So v k bar chi f, which is also v k bar mu f, and also their multiplicities. There, if you remember the notation, it is alpha 1 to alpha whatever alpha r, and their beta 1 to beta r. These are all invariants. Invariant means if I change this operator, linear operator, to the symmetric one, this don't change. That is why they are invariants. So they are invariants because if f and f prime are similar, then all these are same. Invariants are same. That is the definition of invariance. And why similar? That is the relation we are taking to similarity. That means your matrices will differ by like this. If you have a matrix of F and matrix of F prime, they will differ like this: A inverse. That is the relation. And this is an equivalence relation, and this will decompose your space of linear maps into pieces, orbits. They are the orbits. And then we are going to give a nice looking representative from that orbit, and that is the Jordan block. That is how the theorem is proved. All right, so Jordan gave that. Jordan has used, actually in this also group action is used, but it was never mentioned in the linear algebra. When I studied linear algebra in college, my teacher never explained, and he never uttered the word group action. So it became very mechanical studying, calculation, that also. All right, so I will stop, and today we have our exercise sessions, and the next lecture I will try to indicate you how are you going to classify forms, and for that you will need I will need some invariants. So that means the forms, I will need some. See, what are the invariants here? They are polynomials or zeros and multiplicities, integers, and so on. So similar thing, we will have some, we will identify some invariants and use those invariants to classify all Hermitian and skew Hermitian forms. All right. So I will send